For the Introduction to Epidemiology class and the module on measures of association, this is the second lecture segment, rate ratio and hazard ratio. So now we'll talk about calculating measures of association in a cohort study, and the same measures also apply to a randomized trial using person time data. So now our 2x2 table is going to be the exposed or treated yes or no rows and the number with incident disease and person time at risk columns. So instead of having A, B, C, and D all be counts of people in the study, we're going to have A and C still be the count with incident disease or with the incident outcome, but B and C are going to be the sum of person time at risk in each of those exposure categories. So as with the risk ratio and risk difference, again, we can measure association between exposure and disease using a ratio or a difference. So in this case, between the incidence rate in the exposed and the unexposed. So A over B would be the risk, would be the rate in the exposed group, and C over D would be the rate in the unexposed group. So A over B divided by C over D would be the rate ratio. A over B minus C over D would be the rate difference. So for an example of using person time data in a study and how to report it, first of all, just how to calculate it. I'm going to go all the way back to one of the studies by Dahl and Hill of lung cancer mortality and cigarette smoking. And the reason I go back to this paper is, one, we talked about it as an example early in this course, but the second reason is in their published paper, they actually show in excruciating detail their calculations. Today, how you calculate a risk difference and a rate, how you calculate a rate and then how you calculate a rate difference and a rate ratio are considered to go without saying. And in 1956, they didn't necessarily go without saying, so they actually showed all of their calculations. So let's take a look at this. So they're showing the number of men living in each age group at the beginning of each year of the study and the total number of years of exposure. So their person time is over on the right, the total number of years of exposure, or we would call it now the number of person years of exposure. And they also break this out by age because in their analysis and in most analyses of data about human beings, so many health conditions vary dramatically by age, and so we do sort of sort them out and use different methods to account for the age of the population being studied. So here they start with, so let's start with the upper left. In 1951, they started with 10,000 men under age 35, and so 10,000 person years were contributed by men under age 35. And then actually, if you go across from left to right, the number that are under 35 decreases every year. People under 35 are not dying. They are moving up to the 35 to 44 age group. So see how the 35 to 44 age group is growing, going from left to right. So this is just the concept of the number of people that you have in the study, and every time you study, you observe that person for 1 year, there's a person year. So they're adding up and they're showing how they got their person years. And then calculate, this is the next table, another table from the same paper, and this is showing the calculation of the person time data and the denominator by exposure status. So now they're showing how many total person years accumulated among non-smokers in the different age groups, and how many person years accumulated among smokers. And so those are the those two columns with non-smokers and all smokers, and those are the number of person years in each of those age groups and in each of those exposure categories. And as we talked about, smoking was very prevalent in Britain at the time the study was done, so the total number of person years among non-smokers is only 25,250, and among smokers is over 100,000. And they further break it down by the number of person years according to the amount smoked in this table. Okay, and still with Dahl and Hill, now we're going to look at the table in which they show the calculation of the incidence or mortality rate using those person-time denominators. So in this table, there's a column that is the number of deaths from lung cancer, number of deaths. And let's just look at the top row first, which is the number of deaths from lung cancer. So they have 84 deaths from lung cancer. And then they have a death rate, which if we look back at the title, it says death rates per year per 1,000 men, or in other words, per 1,000 person years. So they have 84 lung cancer deaths, which gives us 0.81 deaths per 1,000 person years. And then among the non-smokers, the death rate was 0.07 deaths per 1,000 person years. And in the smokers, it was 0.9 per 1,000 person years. So they've taken those laboriously calculated denominators in the previous tables, and then they've divided their numerator to get their rate. So this is an incidence rate with a person-time denominator. And although they're choosing to label it a death rate, it's the incidence of death, or it's more often called a mortality rate. And and then you can use those rates to calculate rate ratios and rate differences. So if we look at the lung cancer death rate per 1,000 person years, smokers compared to non-smokers, 0.9 compared to 0.07, the rate ratio is 12.9. If we look at another row that was in the previous table, so let's go back to coronary thrombosis, which is the second from the bottom, they show 4.22 deaths per 1,000 person years among non-smokers and 4.87 deaths per person year among smokers. Deaths per 1,000 person. Yes, per 1,000 person year, sorry. And then the ratio of those two is 1.15. So we like to use this example in epidemiology, this particular study and the influence of smoking in general, to illustrate something interesting about the rate ratio and the rate difference. When you use the rate ratio, the rate of lung cancer death among the non-smokers is so low among the unexposed that the rate of 0.9 lung cancer deaths among the smokers is relatively much higher and gives us a very high rate ratio. For coronary thrombosis, the rate of death from coronary thrombosis among the non-smokers is really quite high, 4.22 per 1,000 person years. So among the smokers, 4.87 per 1,000 person years does not give us a very high rate ratio for coronary thrombosis death. However, if we use the rate difference, taking the same two numbers for lung cancer and subtracting them, the rate difference is 0.83 per 1,000 person years. For coronary thrombosis, the rate difference is 0.65 per 1,000 person years. So if these were your data and you were trying to communicate about the effects of cigarette smoking, which type of values, which type of measures would you choose to present? If you really wanted to make a strong point about lung cancer and smoking, that rate ratio of 12.9, people are increasing the risk of dying of lung cancer by more than 10 times by smoking. They're only increasing the risk of coronary thrombosis death by about 15%. But if you go down to the rate differences, it shows that that smoking is responsible for about 1 lung cancer death, 0.83, rounding off to 1 per 1,000 person years. But smoking is also responsible for 0.65 deaths per 1,000 person years among coronary thrombosis deaths. So the rate difference might tell us that the effect of smoking on heart disease is pretty important, whereas the rate ratio, it seems less important. So this is the philosophical dilemma of the investigator. What do you want to say, and how are you going to say it? And it illustrates to epidemiologists that a rate ratio can really present your information in a somewhat different light than a rate difference. All right, so a more recent example, calculation using person-time data and a rate ratio. And this is an observational study of incident rate ratios, and the table is incident rate ratios for disease-specific hospitalizations among children born at term, exposed to preeclampsia or eclampsia without being born small for gestational age. So the exposure categories are in the columns: mild preeclampsia, severe preeclampsia, and eclampsia, and then at the right a total of all preeclampsia or eclampsia. And so they're showing IRR, or incident rate ratios, of hospitalizations for a whole variety of different conditions among those children, and according to the presence of eclampsia in pregnancy. So thinking about the rate ratio, note that the rate ratio is unitless. It is a ratio of two measures: the incidence rate in the exposed or treated and the incidence rate in the unexposed or untreated. So those measures have the same units, and therefore if you take a ratio of two measures with the same units, the units cancel, and the result is a unitless ratio. Similarly, a risk ratio or odds ratio has no units. But a rate difference or risk difference is based on subtraction, and it retains the same units as the measures being compared. So again, when we talked about the Dahl and Hill paper and the mortality rate difference due to smoking, or the mortality rate difference in lung cancer due to smoking, the mortality rate difference in coronary thrombosis due to smoking, those were actual, the rate differences were actual quantities in terms of rates and deaths per 1,000 men. So people, if you have those data, it is actually kind of nice to present them, because the units, and therefore sort of the impact on the population, is retained in the measure. So, and when we're talking about measures of association, the concept of a null or no difference quantity is very important. When the data indicate no difference in incidence of the outcome between the exposed or treated and the unexposed or untreated groups, the result may also be termed no effect of the exposure, no association, or null. So for a risk ratio or other relative measure, the null value is 1. For a risk difference or other absolute measure, the null value is 0. So now we're going to talk about the hazard rate ratio a little bit. In papers, so again, under the general rubric of measures of association using person-time denominators or using survival time data, in papers reporting on randomized trials or cohort studies, the usual measure of association reported based on person-time survival data will be a hazard rate ratio. So the hazard rate ratio has approximately the same interpretation as the incidence rate ratio. It is, however, calculated differently. So a rate ratio or incidence rate ratio are based on the sum of events and the sum of person time across all the time being studied. The hazard rate ratio is based on the ratio of time-specific hazard rates. The hazard rate function estimates the risk of an event in the cohort as it varies across follow-up time. And I have a couple slides coming up that I hope will help explain this. The hazard rate ratio is calculated by comparing hazard rates for two groups at each failure time. And it's calculated using a Cox proportional hazards model. Don't worry at all about what that model is, just a phrase that you'll frequently see, and that is the standard and correct method for calculating the hazard rate ratio. So going back to the hazard rate. The hazard rate itself is rarely reported or shown, but it is the basis of the hazard rate ratio. So the hazard rate function is shown at the right below. It is based on the same survival time data as the proportion surviving or the Kaplan-Meier calculation on the left. So from the same study, the left panel here shows the proportion surviving over time, and we see the proportion surviving drop steeply between time zero and about halfway through the first year. It's just a steep drop in the proportion surviving, and then it seems to be a fairly straight line but continuing to go down. So on the right, from the same data, is calculated a different quantity, which is the hazard rate. So it's the time-specific hazard rate. So this shows us that very close to time zero, the hazard rate is very high. So the number of events per unit time close to the start of the study was very high, and then that hazard rate dropped and then kind of leveled out at about 0.1 per year for the rest of the years of the study. So again, this function on the right, the hazard rate function, you can generate that from Stata from after doing the stset command and the STS graph, and you have to use the right options after the comma, and you can get a hazard rate function. You rarely see it, but I just like to show it to give a little bit of a concept of what a hazard rate ratio is. So the next slide is the same data, except that there's now two hazard rate functions, and the lighter gray line are the individuals who had cardiac arrest during hospitalization, and the black line is those who did not. So this is the hazard rate function in two different groups. And so you can see that it's really one of those groups that had an extremely high hazard rate. So it's the group with cardiac arrest had those extremely high hazard rates in the first year, and the black line, their hazard rate was also high, but not nearly as high. But then after a year, those two groups had a very similar experience in terms of their hazard rate for years 1 through, say, like 4. So this kind of illustrates that treating all the time as one big block of time and all the events as one big block of events in terms of an incidence rate ratio doesn't always completely capture what's happening in a study population, in two different groups in a study population. Because in this case, one group had a very different experience during the first year, and then the two groups are fairly similar in the years after that. So the hazard rate ratio approach is preferred because it's considered a better way, because it considers the time-specific hazard rates. It's considered a better way to compare the groups. So from the same data, from Stata, I calculated the incidence rate ratio, which came out to be 5, and the hazard rate ratio, which came out to be 4. So examples of preventing a time to failure analysis using a cumulative hazard function, which is 1 minus the proportion surviving, or it's the Kaplan-Meier function, and then a hazard rate ratio. So the hazard rate ratio is not directly calculated from this graph, but this is a very common way to present the data when you have a population with varying follow-up times. You show your Kaplan-Meier function, which is the actual calculated cumulative hazard, and then the hazard rate ratio, which is based on the Cox proportional hazards model. So this is from the women's health study. So the exposure groups are the estrogen plus progestin hormone replacement therapy group compared to the placebo group. And so the lighter line in the graph is the treated group, and the solid line is the placebo group. So the study did show that the study main hypothesis was that estrogen plus progestin was going to be protective for some cardiovascular disease outcomes. That proved to be untrue. And in fact, estrogen plus progestin had adverse supplementation, had adverse effects on certain outcomes. Just to be contrary, I selected the graphs for outcomes for which estrogen plus progestin actually was protective. So anyway, that's a little bit too long of a story for this example, but these graphs are showing, these just happen to be two examples where the supplementation was protective for the incidence of the outcome. So they're showing the hazard rate ratio for colorectal cancer of 0.63 and the hazard rate ratio for hip fracture of 0.66. And again, this presentation with the Kaplan-Meier function, and then usually the hazard rate ratios are maybe in a table or something like that. And then below the graph, they show the number of study participants remaining at risk at each time point, which is considered a good practice when presenting data with follow-up over time and where the size of your study population is changing over time. All right, so let me just pause and say, why are we discussing hazard rate and hazard rate ratio? So any kind of in-depth discussion of hazard rate and hazard rate ratio are usually not considered to be within the scope of an introduction to epidemiology course. They're considered a little bit of advanced statistical content. So I am not trying to teach you how to do those calculations, but I am introducing them here because this measure is seen so often in the biomedical literature. And I want to just point out, if you don't remember anything else about the hazard rate ratio, is that unlike the risk ratio, you could not reproduce the calculation from the numbers. So I showed that one example of a randomized trial, and they showed what they called a relative risk, and they showed the counts of the number of participants with and without the outcome. And I plugged those into Stata, and I reproduced their risk ratio exactly. The hazard rate ratio, you could not look at someone's tables and calculate and come out with their hazard rate ratio. It's got this time component, and it's sort of combining a lot of estimates over time. But anyway, so the interpretation of the hazard rate ratio is like the incidence rate ratio. It's a ratio of incidence or hazard in one group compared to the other group.